All right, let's go ahead and get started. Any questions on this? Right, so so this guy here, I want to solve this story. So how do I solve this equation? So algebraically, we can take a base, we can take a log of both sides. So we're basing that. So let's do log base 3 on both sides. So log base 3 of x equals log base 3 of 40. How does that simplify from there? So the left-hand side simply becomes x. So x equals log base 3 of 40. This is the exact answer. Because that's an exact solution. I want to approximate that for different ways. How would I do that? You approximate that power. At least most of you, like the sky calculators, they're probably the capacity as well. You can only take a logarithm of two bases. Natural log, so base e, and what's sometimes called the common log. We can't do that here. So I'm going to do something to solve this. If I take a natural log of both sides, I get natural log of x equals natural log of 40. So the problem here is but using some of the properties we talked about yesterday, it's still solve this equation. We'll go to the left-hand side of the equation and that'll work. If there's something that's a natural log of both sides. The one thing I can do is this. If I have something natural log of 3 raised upon x, that is equivalent to x times the natural log of 3. So, what kind of makes this but all, in any case, give us here, how to solve x. Yep. So x equals natural log over natural log, which is something. Something will be that, right? All that. So let's call natural log of 3 to the x something else. Call y. Basically the same thing. E raised to the power of y. E raised to the power of y. Well, so e raised to the power of something will give you 3. But you multiply that by x. What? All right. So that was not this method right here. Sometimes you'll see it called the change of base formula. So if you have a log base A, not any positive number, you can rewrite that as natural log, or really anything. Could be log base 10 over the log base 10 of A, or really anything else you want. I'm just choosing natural log because it's one of the bases that is easy to calculate. But all right. Any questions? We're going to need this idea to find the derivative of your kind of basic log function. One thing I want to remind you of, and I think I've showed you so now we're going to use both of those ideas to find this derivative. I want to find the derivative of generic log function. So any base. So how do I find derivatives? So all derivatives come from this difference quotient. Now I'm going to fill things in for the specific function I want, which is log base A. That's all right. Explanation. Yep. So yeah, since I'm subtracting logs, I can treat it as a single log. Log base A of their quotient x plus h all x. And from there, I'm going to rewrite the inside of that to be log base A of 1 plus h. All right. Do it so far. I don't think I'll know why I'm doing it. So far, you I'm going to multiply top and bottom of this fraction by doing that. X over h. Log base A. I can bring that up. And I write this in a string way, and I write this as 1 over h over x. Can I take this limit now? Well, maybe I should ask, am I okay to do the thing that is it? I have a log, so multiplying that log by x over h. Same as me raising the power. So from there, I have this log there. Let's focus on the non-logarithmic part first of all. I want h to go here. So the inside of this, right, here's the go. What's going to happen to 1 over h over x? The h is going to go that's a good part. So you have a number being raised to a power thing. That thing actually is. I'll back up just to kind of point it out to you. We know that. Which means I can evaluate that limit, and that limit becomes log base A of E over which for now I'm at times log base A of E, which if we do that base change relationship, we're going to come sides of it with this. 1 over x times the natural log of E over the natural log of A. So this is something that's totally available for our use now, but that is derivative of any log or yeah. Yep. All right. So rule you can use now the derivative of any log function. So 1 over x times natural log of A. So can we apply that to specifically the natural log of x? One over x times the natural log of something, right? What's the base of the natural log? So 1 over x times 1 over natural log of A. So this derivative is another reason why when we're dealing with calculus functions, knowing what base is. Any other questions? All right, let's do a couple of examples. Want to find the log base 37 of x. Or I don't want to find it, I want to take the derivative of it. So based on the rule we just went over, what would that derivative be?
X 37.
1 over x times the natural log of 37. And that's pretty much it. It's to be 1 over x, and then basically times 1 over the natural log of whatever the base is. Any questions there? All right, let's get a little more complicated. F of x equals log base 2 of x squared plus cosine x. So how do we have to think about handling this one? Or can we just write down what the derivative is?
Did that change it?
Does what change anything?
X squared plus cosine x, like, just because it's more terms or squared.
Do we think it changes something? Solomon says no. Garrett? What if we're going to use product rule? What are the two things that are multiplied together? So that log is not actually being multiplied by anything. I'm taking taking the logarithm of something is not an act of multiplication.
Oh, this would have to be, is this chain rule?
Oh, you meant chain rule? Then I agree. Yeah, so it's not, we're not multiplying two functions, we're composing functions, right? So let's say that f of x is equal to, are we gonna get away with two functions or do we need more?
2, yeah. 2, yeah, because isn't it addition from the second one, so can't just take that.
Yeah.
Yeah.
So let's try it with two functions. Based on this definition, what is g?
Log 2 x.
So outer function log base 2 of x. Inner function is
X squared plus cosine.
x squared plus cosine x. So now we can find derivatives, right? What is the derivative of g? 1 over x times the natural log of 2 and h prime.
2x.
2x minus sine x. All right. Probably should have asked this, but do we agree that the function I gave you is equal to g of h? G composed with h?
Yeah.
Yeah, should be good, right? So I agree that chain rule is the way to go here. So now I think we have all the parts we need to write down what this derivative is. So what is it?
One over x squared plus cosine x times the natural log of 2.
1 over x squared plus cosine x times the natural log of 2. And then what? Sorry, what was it? Times what?
Times 2x minus x.
Times 2x minus sine of x. And I will condense this a little bit. So 2x minus sine of x over x squared plus cosine x times the natural log of 2. And I feel like I'll give you a reminder here of how we use the chain rule here. Took the derivative of g, evaluated at h, then multiplied that by the derivative of h. Yeah, so you have composite function there, so have to use the chain rule. Any questions about this specific one here? All right, moving on. X to the 13th natural log of X. How would I handle the derivative here?
This one's product rule,
Why is it product rule?
because you're timesing you're multiplying two X's together.
Yeah, so you have two functions of X that are being multiplied together, right? So this time I don't have f of X equals g of H, I have f of X equals g of X times H of X. So we should be specific about what G and H are. What are they?
13x to the 12th.
No. I think I know what you're, yeah, you have to know what you were getting at was
Oh, yeah.
the derivative,
Yeah.
which is 13x to the 12th. And then H prime would be 1 over X. So from there, we should have everything we need to go for the derivative. So what's the derivative going to be?
13x over r12 times ln x.
So part of it, so first term is going to be 13x to the 12 times the natural log of X. And what's the rest going to be?
1 over x times x to the 13. Plus 1 over x times x to the 13.
Yeah, which is what?
X to the 12.
Yeah, plus X to the 12. How are we doing? Okay. All right, any questions before we move on? All right. Want to find DGDU. So how do we have to handle this one?
Quotient rule.
Okay, quotient rule. So now we're saying that G of U is equal to, call it A of U over B of U. If nothing else, quotient rule is a little simpler to see how to define these things. What is the derivative of A? 1. How about B?
Oh, 1 over e.
1 over U. Okay. Now, based on that, can we go for DGDU?
So 1 plus ln u.
Okay.
That's just times the 1.
Yep, so I'll be specific about this just in case we're getting lost on the order. So A prime of U times B of U minus A of U, B prime of U, all over B of U. So A prime of U we said is 1. So first term is going to be 1 plus natural log of U.
Is the second term 2?
Second term should 2.
Yes. U over u plus. No, sorry.
1 over U plus 1, right?
Yeah.
All over 1 plus natural log of U squared. Do I get anything that simplifies? Sort of. Natural log of u minus 1 over u all over 1 plus natural log of u squared. Gross?
I hate using u as a variable.
Yeah. It's a choice. It's not always a good one. Other than that, let's go to the plants here.
Other than that,
Okay. Any questions before we move on? All right. I'll try to find y prime for this. This is not natural log of x. This is a little bit different. So let's talk about this first. If we have a function natural log of x, what's the domain for that function natural log? All real numbers? Cannot take the natural log of all real numbers. So if y is equal to natural log of x, then that's the same thing as me saying x is equal to e to the y, right? If I take a positive number e and raise it to some powers, any power you want, what kinds of values will you get for x? Or more to the point, what kinds of values will you never get for x?
You'll never get negative.
You'll never get negatives, right?
Because it'll always stay with 0.
It'll always be positive. So because of that, the natural log function has a domain of positive numbers, right? But that's not what we have. We have f of x equals the natural log of the absolute value of x. So if I take the absolute value of x, will this function be defined for, or yeah, will this be defined for all real numbers?
No, so the absolute value has to be positive.
Right? So what's going to cause that not to happen? Like, I think now I can throw negative numbers in there, right? Negative 10. If I take the natural log of the absolute value of negative 10, that comes up to the natural log of 10, which is defined. I still don't think the domain is all real numbers, though. Why not? Still not defined for 0. The absolute value of 0 is not positive, so I can't take the natural log of that. So all that to say that this function I'm giving you, this y equals the natural log of the absolute value of x, this has a domain of all real numbers except for 0. So let me jog your memory for something else we've done in the past. We have said this before. The absolute value of x is equal to, this piecewise thing. It's equal to negative x if x is less than 0. It's equal to itself if x is greater than or equal to 0. Let's stop there for a bit. Do you remember defining absolute value like this? Whether or not you remember, let's make sure we're okay with it. If x is positive, what's the absolute what's the absolute value of 10? 10, right? So if I want to take the absolute value of a positive number, I just take an absolute value, I just take the number, right? But if I want to take the absolute value of a negative number, for example, negative 20, what is that going to be? 20. It's negative 20. So for the real numbers, it's pretty simple. If it's a positive number coming in, you just pass it along to the output. If it's a negative number coming in, you flip the sign and then pass it to the output. So based on that, I can say this: y is equal to the natural log of negative x. if x is less than 0. And the natural log of just x if x is greater than 0. Can't be equal to 0, but I can split it up that way. Thinking back to the absolute value. The absolute value function we said was continuous everywhere, right? But is it differentiable everywhere? Not at 0. Everywhere but 0. So we know the absolute value function is not differentiable at 0, but maybe we can say something stronger about it in this case. We know the natural log of the absolute value is going to be defined there. So it clearly can't be differentiable, but maybe it can be differentiable everywhere else. So now let's do this. Let's take the derivative of both of these pieces of this piecewise function. What is the derivative? Actually, let's start with the easy side. What is the derivative of the natural log of positive x? 1 over x. So 1 over x if x is greater than 0. What is the derivative of natural log of negative x? What's that? Is it 1 over negative x? Think about what you have to do to take the natural log of negative x. What if it was something more complicated? What was the natural log of like 25x? Or 25x squared? Think about what you would have to do to deal with that derivative. I think we did one just like this a few examples ago. So not a natural log, log base 2, but this time you had a log base 2 of something more complicated than just x, right? So because the inside there was more complicated than just x, what did we have to get involved? We had to use the chain rule because we're composing functions together. So you have the same kind of thing here. So let's kind of unite that to natural log of x. What's the derivative of natural log of x? You told me it was 1 over x, right? Well, I really should focus on chain rule, right? So what's the derivative of x? What's the derivative of the inside function?
Oh, 1.
Just 1, so 1 over x times 1. Doesn't affect anything when the inside function is just x, because the derivative of that inside is just 1. Here we don't have that. So I believe the derivative of, if you're just looking, think about this in terms of inner and outer functions, the derivative of the outer function would be 1 over whatever the input is, right? But now I got to multiply that by something. What is that something? What is the inner function to the natural log function here?
Negative x.
Negative x. What's the derivative of negative x?
Negative 1.
Negative 1. And this is something that's kind of mysterious about natural logs. I'll give you one more example that's kind of weird. What is the derivative of the natural log of, someone pick your favorite number?
12.
1210, 120x. What's the derivative of a natural log of 120x? What does it seem like it should be? So let's break it down in chain rule, right? What's the derivative? So let's treat the outer function as natural log. What's the derivative of any natural log function?
1 over x.
So 1 over x, except the input in this case is 120x. What's the derivative of that inside function? So the derivative of any natural log function that's just like some constant times x is 1 over x. So very, very counterintuitive, but it's true. So now what I have basically is I have the derivative of this function is 1 over x. Basically everywhere is defined.
Except at 0.
Yeah, well, the original function's not even defined there. So y prime is just simply 1 over x. But I'll point out x for x not equal to 0. Even though the function's not even defined there. Solomon?
Did we need to do that if we know that like an absolute function is mirrored over the y-axis? So the rate of change isn't changing as like if it whether it's negative or positive, the x values. Like, do we even have to find that for less than 0?
Yeah, in general, yes. You can't rely on this being the same because where can I find some room? Delete this. Let's think about what the derivative or what the function. If I was just in a graph y equals the absolute value of x, you can think of this as 2 straight lines, right?
Yeah.
One that acts like this and one that acts like this. What is y prime for x equals -1? And what is y prime when x equals 1? What's the slope of the tangent line where x equals 1?
Oh, wait. No, for 1.
I don't like these numbers. They're gonna hide what I'm trying to show you. I'll do -3 and +3. What's the slope of the tangent line to this function when x equals 3? 1. What about -3? -1. So they're different here, right? So this is going to show up, and those of you who are moving on to Calc 2, which is probably all of you, but I want to assume, this shows up in an idea when you're taking what's called an antiderivative. All right. Go ahead and move on. I'll take the derivative of this nasty thing. And I can already hear the sounds that you're scared of. So based on what we know right now, how do we have to deal with this thing? Do we need product rule? Why?
The numerators multiplying.
Okay. You said the word numerator, which means there's probably a denominator.
Yeah.
Which means product of a chain rule, or quotient rule is part of this. We have to do chain rule.
Yeah. Yep. Because the power of 750.
Yep, it's totally possible to use all those things to get a good derivative. I'm not going to do any of that. So what I'm going to do instead is take a natural log of both sides of this equation. That gives me a natural log of y equals the natural log of this beast that some of you guys were grinding your teeth at the moment you saw it. What is the point of me taking a natural log of this thing?
Will it get rid of the square root and the exponents?
It won't get rid of them. They'll still exist, but I think you're on the right track, but I'm not sure. So you all said that product rule and quotient rule is going to have to be a thing, because I had these two quantities multiplied in the numerator, then divided by something else. This binomial in the denominator is raised to the power of 750. But here's what I know I can do because of how logarithms behave. I know that if I'm taking the log, any log base, of terms that are multiplied together, I can basically add them. I can basically just take their logs individually and add them. And similarly, I can subtract when I have division. So I'm going to rewrite this whole thing like this. The natural log of x squared minus 7 plus the natural log of the square root of x to the 5 halves plus x minus the natural log of 2x plus 9 to the 750. Do you have to use product rule now? Quotient rule? No, we got away with it. We got away from doing it. Can we take a derivative now? I mean, you still got to do chain rule because you have these exponents, right? Do I have to keep those exponents the way they are? Think about the way exponents behave when you're dealing with logarithms. What's the power on this? So square root is really the power of what?
Half.
1/2, right? So instead of me taking the natural log of all this stuff raised to the 1/2 power, I can take the natural log of all this stuff and multiply that by 1/2. Similarly, I can, instead of taking the natural log of this whole thing, I can take the natural log of this thing and then multiply that by 750. So I haven't taken any derivatives yet. I'm just kind of, I have done a little bit of algebra to trade my nasty, nasty derivative for a few much less nasty derivatives, right? Okay, now I can take the derivative of both sides. With respect to what variable?
X.
I want to take with respect to x, right? So what is the derivative of natural log of y with respect to x? This is, again, this is a chain rule thing. X goes through some function f, and what comes out is y. I don't really understand how y is a function of x. Well, I do because it's written there. That nasty thing is how y is a function of x. But I can instead think of it this way. X through function f gets transformed to y, and then y through some function g gets transformed into natural log of y. Do we know what the derivative of that function g is?
1/x.
1 over y.
It'll be 1 over y in this case because the input's y. So if we're doing chain rule, you kind of got to handle this one layer at a time. So the outer layer, the derivative is 1 over y. What's the derivative of the next function, f? It's the derivative of some function that turns x into y. So all you can really say about it right now is that it's dy dx. Which is fine, that's really what I want, right? That's what y prime is dy dx. For the rest of the stuff, they're all added and subtracted together, so I can take their derivatives individually.
Is that 1 over y times dy dx?
Yes, that's a chain rule. So when I take the derivatives one layer at a time, I basically, the chain rule is the product of all of them. In this case, there's just 2. What's the derivative of natural log of x squared minus 7?
Is it 1 over x squared minus 7?
The derivative contains 1 over x squared minus 7 because that is the quote unquote outside function. So the natural log, so the derivative of the natural log of something will always contain 1 over that something. I'm not going to say it's equal to that, but it contains it. What else has to be involved here?
Can you multiply 2x?
Multiply by 2x and most importantly, y2x.
That's the inner function.
It's the derivative, that's the derivative of the inside function. Yes. So that's the derivative of that first term. This next one's going to be 1/2 times something. What's the derivative of the natural log of x to the 5 halves plus x?
Plus x times.
So yeah, first it's always going to be this basically, we know the derivative of the natural log function is 1 over the argument. The argument is just the thing you take natural log of. So that it contains that multiplied by
5 over 2x minus, no, 5 over 2x to the power of 3 over 2.
Yep.
Remind me one more time how 3 comes out of 5 halves?
How what?
How 3 over 2 comes out of 5 halves?
3 over,
You
oh,
can always minus it. 1.
Yeah, so power rule, bring down the exponent,
Right, subtract the half and you're left with 3 parts.
but you do not subtract the half, you subtract,
The 1,
you always subtract 1, so 2 halves.
right. Okay.
5 halves minus 2 halves. And I think you said +1, but I'm gonna go ahead and write it down anyway. So that's the second term. Got one more.
1 over 2x plus 9 times 2.
Minus,
Sorry. No, I'm joking.
there was something else we lost.
Oh, minus 750 times.
Yeah, so minus 750 times 1 over 2x plus 9 times 2. So still pretty gross, but we didn't have to do product rule and keep track of like the 6 or 7 nested functions you have to keep track of to do that the way that you were worried about. But now I got 1 over y dy dx. Does anything clean up? Kind of. Oh, that's not, that doesn't cancel anything next to it. So 2x over x squared minus 7. Garrett?
5x 3 over 2 plus 1 over 4x 5 over 2 plus 6.
I believe you say it again.
5x 3 over 2 plus 1 over 4x 5 over 2 plus x.
Good. And then this one comes out to be minus 1500 over 2x plus 9. Are we done?
Yes.
No.
No,
So what are we after? Like, what's the thing we're trying to find here in the end? dy dx. We're so close. What do we have to do? You gotta multiply y to both sides. So I'm gonna multiply y to both sides, and I'm gonna cheat a little bit because I'm out of room. What is y? I don't want to have a derivative dy over dx in terms of x and y. I would love for it to be totally in terms of x. Y is the thing that we started with. X squared minus 7 times x to the 5 halves plus x all over 2x plus 9 to the power of 750. That is dy dx.
Would you ever put a problem like this on the test?
I might,
Multiple choice.
probably not. So here's the thing, I mean, I don't have time to get into a new example. We got 2 minutes left. I'll ask you, think of I have it on video, so I can actually compare this. The first time I asked you to do anything using quotient rule probably took us a few minutes. And if I threw that same thing at you, 100% chance none of you remember what that example was. I don't remember what that example was. But if I gave it to you right now, you'd probably do it in 20 or 30 seconds. So this kind of thing is not really that different. The first time we go through it and we see it and we do it carefully, it should be nasty, right? You'll practice it, you'll get better at it. There's a bunch of these on the 3.3 web work. The last one will go a lot faster than the first one. So all that to say, if I drew something that was similarly complex to this on a test, I would think that'd be reasonable. Having said that, any questions about this specific one here?
How do we know it's done? Like, we don't have to add and subtract the things in the bracket.
Oh, I mean, I could tell you to simplify it, but I have no idea like what that simplified thing would even look like. So as far as for how we're done, all I asked you to do was differentiate. So all I really asked us to do was to find dy dx. You could probably do, like, if you want, we can find a common denominator of all those terms.
So
No, I have no desire.
as long as we can differentiate anymore.
Yeah, in fact, I mean, that's a pretty common thing in calculus, is especially like from a teaching perspective. I believe you've all been simplifying things for years. I really need to know that you can differentiate and use those derivatives. That's what I'm looking for. Yeah, if I said differentiate and simplify, we'd have to keep going, but I don't even know, like, just based on all the things in there, I don't even know what a simplified version might look like. Any other questions? All right, stay dry if you can. I'll see you Friday.